Welcome back. We're going to be heading into the final topic of Chapter 4 now, which is called Voronoi diagrams. Though for a long time we've been setting this one up, and now we finally get to put together all the skills. Midpoints, distances, slopes, equations of lines in different formats, parallel lines, perpendicular bisectors, points of intersection. Everything comes rolling all together now, and we're going to need all of those skills for this final application. Okay, let's take a look here. I got a little introductory video I found on YouTube. I'm going to play it right now.
Hey, what do all the images that you see behind me here have in common? Perhaps they're all animals? No. Perhaps they're all living things? No. What they have in common is that they share a common pattern called a Voronoi pattern, named after this guy. And as you can see, Voronoi patterns are very, very common in nature. They're also not too hard to create in a computer, so they make a great tool in your artist's toolbox. So let's find out how to make them. The basic idea behind Voronoi.
Okay, that video was from a programming YouTube channel. So he's trying to code how to do this kind of thing, but that doesn't matter. We're not doing any coding. But there he was just showing you many places that Voronoi patterns show up in nature, and we're going to try and solve real world problems using it. Let's take a look at this slide here. It says there are 5 airports in the state represented by dots on the diagram. The colored regions on the diagram indicate the points which are closest to a given airport. Think of it kind of like, I don't know, you got like a world's worst roommate, and you like put a line on the floor to separate it, except it's not one roommate. It's like multiple roommates. And you got to come up with a fair, equitable, reasonable, agreed upon border between them. So it needs to be just as far apart from one another. It needs to be perpendicular to the line that connects you, indicating that it separates all the points the same distance apart. But that's fine if it's 2, but when it's 3 or more, you got to be really careful, and you got to apply some decent mathematics to it. So for example, this is going back to the text here. Airport 5 is closest to all points in the purple region. Yeah, you can see that down there. And Airport 2 is closest one to all the points in the green region. All right, so what would you use something like that for? I suppose if you were trying to decide where you wanted to fly in or out of, and you were nearer to one airport than another, or perhaps sort of in between two, you could find out exactly where. This is also used in telecommunications and other places, so that information is directed to the nearest port. Perhaps it's a sales office, or something like that, a distribution center for some sort of commodity that's going to be distributed through a region. This is an example of a Voronoi diagram named after George Voronoi, and there's many applications, as it says there. Here's one that I've sort of mentioned about a couple of times in class. Existing borders, sort of territorial borders between places, often are shaped by history, or geography. Perhaps there's a river that dictates where a border should be, or some sort of other space like a canyon or a mountain range or something. And it could just be historically what was decided upon once upon a time, but it mightn't necessarily be what is best now. And so sometimes you want to rethink those borders. Okay, let's just continue here. I got an example.
Hey there, everyone. Welcome to our very first Voronoi diagram. Hope this is an exciting application here. It's something that you probably have never seen before. I haven't seen it in many years, but it's a lot of fun to create. The applications for this are usually, well rooted in reality-based problems, trying to, some sort of urban development thing, trying to locate a new, coffee shop if you're an entrepreneur, or maybe if you're a city planner trying to find a better place for a garbage dump, away from people. There are, significant practical applications to this, and let's just see how we can extend our knowledge of geometry from the Cartesian plane to one of these problems, and I hope it works out pretty well. I'm going to start us off with one of the more basic kind, which is to separate 2 ordered pairs on the Cartesian plane. Essentially what it comes down to is this. We're trying to set up a border or a boundary between those 2 points, where every single point that's not on the boundary is either closer to A or closer to B. It's almost as if you were like, you're living somewhere and you're choosing an airport, a preference, you want to have a shorter drive to an airport. And so you would sort of draw a line on the map and figure out which one is closer. Maybe that would be a preferable airport to attend. Okay, so what do? We're trying to look for a line that's going to more or less run in this direction here. Now, I'm sure if you've been paying close attention in class, you'll know that this is going to have to do with the realm of perpendicular bisectors. So to do that, it starts off with finding the midpoint right here. And I'm going to remind us what the midpoint formula is. I just dumped it down over here. I need to find the midpoint of these 2 points A and B and highlight it somewhere, and there it is. So its coordinates are -1, 2, and again, that's just putting the x values in here, the y values for A and B in here, dividing them each by 2, and coming up with those values there. So we're not all the way there to finding a perpendicular bisector. We still need to find its slope. But its slope isn't something that we just guess at or are visually inspired by. It's calculated, and it's related to the slope of the line that connects A and B. It's perpendicular. So the slopes of those two lines will be negative reciprocals to one another. I'm going to put the slope formula back up there. There it is. And so we take a look at the input values for A and B into the formula. And we've done this a number of times this chapter, and you work out the value of the slope. Once you do that, you know that the point -3, 3, or conversely 5, 1 are on the line. So we're going to use the slope. We're going to use the slope point format of a line and enter the information there, and then we'll be able to have a nice little graph of it. And let's see, when I use the slope formula on the points A and B, I can see that the slope is -1/4. There it is. And, well, that's the equation. And I've only shown a line segment. I've only connected A to B. These actually go on forever in both directions, but I'm not interested in that much real estate. I just want to have enough of it so I can see where the perpendicular one goes. So if the slope of the line that joins A to B is -1/4, then the slope that I want must be +4, namely the negative reciprocal to that line. What do I do with it? I put that information along with the information about the point -1, 2 into our slope point format of a line, and I come up with that right there. And again, like before, this is just a small piece of the line. It's a line segment. It has a finite beginning and end. Normally lines don't have an end or a beginning. They just go on forever in both directions. I'm going to take away some of the other information here that I don't need. Take that point away, take away the label. And you can see now that this is our very, very first Voronoi diagram. Ideally, the line would be longer, and you would know that every point that's not on the line is either closer to A or is closer to B. All right. In our next video, we're going to see what happens if a third point joins the group.
Okay, so Voronoi diagrams, practical applications. Soap bubbles. You may have seen soap bubbles trying to pop in the bottom of a sink or something like that before, and they take on this kind of shape. And there's just so many. And you can hit pause and read that paragraph there. But here's an example of another Voronoi diagram. Basically, we're coming up with a zone around the points, which is closer to it than its neighboring points. But the skill is how do we actually create them? Here's a nice little diagram. It says, or a nice question from a different textbook. Use a Voronoi diagram shown. Identify the site closest to 320. Okay, so I've popped a little point there on 320. This looks like it might be an exam question. I don't know. Voronoi diagrams are new to the syllabus this year, and it's not been an examined course yet, so we don't really 100% know. So we're going to get you prepared for everything that we think they might ask. Give the coordinates of the vertex. 4 equidistant sites. What I would notice here is that 4 of these edges, 4 of these straight lines met right here. So I have to conclude that all 4 of these points here must be equidistant from it. Estimate the coordinates of a point equidistant sites A, E, and K. I would guess it's probably in around there somewhere. It would have to be on the line. The perpendicular bisector that separates A and K, I would guess around there somewhere. Hard to say exactly. And explain why the diagram cannot give a point equidistant to sites C, F, I, and L. Well, B is in the way there. There's no perpendicular bisector between I and L, so it's impossible to say what's going on there right now with the diagram as it is. Now, you will have to hit pause here and read this, because this is the sort of the official guidebook as to how you develop a Voronoi diagram. I prefer the experiential way, watch, repeat, extend your knowledge. But if you were following it like a recipe from a recipe book, this is what it looks like. So hit pause, and when you finish reading that, you can hit resume.
All right, back to our own Voronoi diagram creation. This is where we left off. We had a nice little orange line there dividing the space up between the sites. We call them sites A and B. And now you've already seen the incremental algorithm. I mean, it's increasing, it's building. As more data comes to the playing field, we have to accommodate it. And specifically in this case, what happens when a third point comes in? So I'm gonna pick a third point. There it is. I'm going to give it an appropriate label. The first thing we do in the incremental algorithm is we decide which side of the first borderline, the borderline between A and B, is it on. And that's pretty clearly it's on the A side. So I start my focus on creating a new boundary between A and C. We will eventually get to B, don't worry about that. But for now, our focus primarily is with A and C. It's like before. I'm trying to imagine the line that connects A and C, because I need to split that both in half and then cut through it perpendicularly. That new line will have a relationship with the existing orange line that we need to sort of decode. And like before, we find the midpoint. I can see here, if I enter these coordinates for A and C into the gradient or slope formula, I can see that slope is going to be, -5. And I then take the coordinates of this point here, which is -2.5 and 0.5. And I can put it into here and get the equation of the line, and then boom, I've got it. Now, once I've got the perpendicular bisector drawn, added to my Voronoi diagram, I can go back and remove some of this information that's not relevant anymore. I just needed to know where that bisecting line was going to come from. Okay, so we can start to see this thing emerged. After I've done that one, now I turn my focus over to point B and its relationship with point C. And I do it for all of the points. If this was a more complicated Voronoi, I would do it with all the points that are in the general vicinity of point C. Okay, first things first, I'm going to draw a little line segment that connects the two. I got to work out the equation of the perpendicular bisector, and that starts with understanding about this purple broken line. I need to know its slope first, and its slope is, let's see, I put the coordinates for C and B into the equation, and I see that its slope is 3/7. If I go ahead and enter those numbers in, and the midpoint is going to be over here at 1.5. Remember, use the midpoint formula over here. 1.5 is the average of the x values, and -0.5 is the average of the y values, and you've got your coordinates there. So if the slope of the purple broken line is 3/7, that means the slope of the perpendicular one is -7/3. And I take that along with the coordinates of this midpoint, put them into the formula, the slope point form, and I find the equation of the line, and I pop it in. Now, this is not surprising to people with experience with Cartesian geometry that those three perpendicular bisectors meet at a single point. We've seen this recently in class, where this is called the circumcenter of the circumcircle. And that basically means if you were to locate the point there, which is inside the triangle, all of the points A, B, and C are the same distance from it. Now, I'm going to go back and I'm going to remove some of this information and discuss why that would be true. Since when you're on this line here, and I'm going to highlight it, that line there, all the points between A and C are the same distance from each other. But all of the points between A and B are the same distance from all the points on that line. So if you're over here at this point in the middle, that means A and B are the same distance, but A and C are the same distance. Since A remains A in both of those comparisons, the contrast is obvious. That point in the middle there is the same distance from A, B, and C. So therefore, there's a circle that connects them. And that, at its heart, is what Voronoi diagrams is trying to get at, not the circle itself. Okay, now, I've got the lines I need. What do I do with them? Well, I need to only keep the parts that really sort of split up Cartesian space. I've got all these lines, part of them are good and part of them are bad. So from the middle there, I'm going to extend out away from A and B and extend out over that way so that the next sort of destination does split between the 2 points. So if I were to do the top one there, you can see I've highlighted it in red, and I'll go back and I'll remove the tail end of it because it's no longer relevant to us. And if I wanted to do the one between A and C, I've got that part there from the intersection of the three perpendicular bisectors out between the 2 points and extending off into space. And I can remove that line there. And lastly, the one that extends down between B and C, and I can remove the tail bit of it there. And now what you see is I entered a new point into the, I'm going to take these points out of the way to make it a nice picture for us, and there it is. So that I've now taken away that orange line that started off this video, and I've added a vertex and created some new perpendicular bisectors because of it, and then adjusted the lines. That's basically it. And now we need to practice this. We need to become good at doing this for sure. And there's also, rules if you want to extend, if a fourth point comes to here. Then we need to practice that today, and we're going to practice it again next time. And then we're going to take a look at the principal application of why we even have Voronoi diagrams in the day after that. Okay, good luck.
Right, so let's take a look at this question here, which I also found from a different textbook. A new site W. Now what they're going to do is they're going to put a new point on this existing Voronoi diagram. It's at 1515. Now 1515 is right around, I think it's there. I think that's where I'm pointing. And so what would be the cell, or which would be the site? You can see which cell it's in. It's in this cell here. But the site that's nearest is F. Next question, find the equation of the line. So you just basically got to find, if it's the separating W from site G. Now, if W is over here, you can see that this line right here, and you'd have to just go find, that would be the perpendicular bisector between F and G. And you can do that on your GDC calculator, and you would see that that equation is y equals x plus 8. Ask for my help if you don't really know how to do that. So then you could, again, add these to your graphical calculator, and you're going to show you how, we can look at how, if W was included here, how do we go ahead and create space for it? Basically, what you would do is find the perpendicular bisector between it and H, it and G, it and C, it and B, it and F, and you would end up carving out a space between some new bisectors, and all the ones that are inside that cell that you create should be removed. There is that point. And so you can see now that this is what it would look like, and you can go ahead and give that a stab on your GDC calculator or on Desmos or some other place. But basically, how do you go ahead and find it? I've created some new perpendicular bisectors between W and H, W and G, W and C, W and B, and W and F. And it's got 1, 2, 3, 4, 5 sides to this little cell right there. Okay, from the syllabus. Voronoi diagram, sites, edges, I'll get into that in just a moment. Adding a new site to an existing Voronoi, that's creating new perpendicular bisectors, and then separating out the new cell appropriately. The application, it's called the toxic waste dump problem. It's a classic math problem. We'll take a look at that later on this week. And there it is. Now here's some of the vocabulary. Where those lines meet, those perpendicular bisectors, we call that a vertex. It separates the line separating the two different the boundaries basically are sometimes also referred to as edges. You can be ready for both of those. The ordered pairs that started it all off are referred to as sites, and the regions in which they reside are called cells. You need to be aware of that because questions can be delivered to you using this kind of vocabulary only and not with a diagram. You need to know what the heck they're talking about. Now, here's another question. I'd like you just to hit pause. I'm not going to narrate through this one, but you can go ahead and hit stop and just think about what is going on. And this is an evolution of how a new site is added to an existing Voronoi. So you won't hear my voice for a little while, but go ahead and hit play and pause, play and pause, play and pause until you understand what's happening in these pink diagrams. Okay, now one more little question here. It says sites SPQ, Q is not shown, and R in the Voronoi diagram represent locations of telecommunications towers. Exciting. Grid units are kilometers, so every time you see numbers here differing by 1, that means it's 1 kilometer. Site Q is missing. Just go ahead and write down the coordinates. Well, Q must be in this unnamed cell over here. And since there's this red line here, it must be the perpendicular bisector between Q, the missing point, and P. So I would say that Q, therefore, must be at the point 4, 1, just to make it balance off against point P. Calculate the area covered by the telecoms tower located at site P. So that's the area of this triangle here. Area of a triangle is 1/2 base times height. Or there's a trig solution that you looked at last year. And it says find the distance between the point 92 over there and the nearest telecommunications tower. Now I know the nearest one must be R because we're in the cell that's sort of highlighted by the site R. So I just want you to find the distance between these two, and I know that that's the closest one, and I could just go ahead and figure that out using my GDC. Here we go, 4I, questions 1 and 2. They're kind of long questions, so don't get deceived here. This takes a little bit of time. Okay, good luck.